Now, how to obtain the state model when the system is described by a signal flow graph? Signal flow graph is a graphical representation of the system. So this actually connects input and output, and there are various forward paths and feedback paths. So this is called a signal flow graph. Now, how to get a state model? Because our interest is to obtain the state model for a given system, and that system is described by a graph. So the number of variables you can see here, the nodes are variables in the signal flow graph. So when you look at x1 dot, because the x1 dot is a differential state variable, this x1 dot is given by 1 by s into x2 dot. x2 dot. So x2 dot is nothing but differential state vector x2. So this can be written as 1 by s. x2 dot can be written as s into x2. So x1 dot is nothing but x2. Now the another variable x2 dot, here you can write this as x2 dot can be written as 1 by s into x3 dot. 1 by s into x3 dot. So this is again 1 by s into s times x3. ss gets cancelled. So x2 dot is nothing but another state variable x3. Now when you look at this variable x3 dot, this is equal to 2 into input. So this is 2u. Then what are the other terminals that are coming to this node x3 dot is from x2 dot. So I can write this as minus 2 x2 dot. Then this is also connected to x3 minus 4 x1 dot. Then this path is also connected to x3 minus 6 x1. So this many terms comes into picture for x3 dot. So this I can rewrite as 2u minus x1 term first. Then this x1 dot is nothing but x2. So I can write as minus 4 x2, and x2 dot is nothing but x3. So I can write this as minus 2 x3. So this is the way the x3 dot can be obtained. Now the state model will have x1 dot, x2 dot and x3 dot can be written as, the first two rows are very easy to obtain by looking at x1 dot equal to x2 and x2 dot equal to x3. So I must have first row as 0 1 0 and second row as 0 0 1, because you have state vector as x1, x2 and x3. So that relation should be satisfied. x1 dot is equal to x2 and x2 dot is equal to x3, and the third row of the state matrix should be obtained from this equation. The coefficients of x1, x2 and x3 is minus 6, minus 4 and minus 2. So state matrix is completed, plus the input matrix. By seeing 2u, there is only one term. So 0, 0 and 2 is the coefficient here, multiplied by input vector. So this is known as state equation you could get. Now the output equation. Output equation means y is the output terminal here. So this y, you can see y is written as 4 times x1. That is one of the path connected, and there is another path connected to this y. It is coming from x2 dot. x2 dot multiplied by 8 is also connected to y. So plus 8 x2 dot. So 4 x1 x2 dot can be written as x3, another state variable. So I can say that there is no x2 term here. So I can write 0 x2 plus 8 x2 dot is replaced by x3. So you can get this y output matrix is equal to C, that is the components of the C are 4, 0 and 8 multiplied by x1, x2 and x3. So this is output equation, and 4, 0, 8, this matrix is known as output matrix. So when signal flow graph is given, write the variables with the connecting paths and then form the state equation as well as output equation in this form. This is a signal flow graph. Again, system is given by a signal flow graph which consists of input variable u and the output variable y, and there are state variables. If you look at this nodes, x1 dot, x2 dot, x3 dot are given as differential state variables, and again x1 and x2 and x3 are there here. x1, x2 and x3 are the state variables. Now our interest is to write the output equation in terms of variables and also the state equation matrices needs to be formed. So when you look at the output variable here, this is y, and you can see there are 3 branches connected. 3 branches are connected here, 5 from x1 node, 10 from x2 and 15 from x3. So I can write this equation 5. So all are approaching y. So 5 times x1 plus 10 times x2 plus 15 times x3. This is the output equation. So now it is easy to get the output equation of the state model, that when I say y is equal to the coefficients of x1, x2 and x3, you can get 5, 10 and 15, and the dimension is 1 row and 3 columns, 1 cross 3, and 3 state variables x1, x2 and x3. Easy to get the output equation from the given signal flow graph. Now let us get the relation between differential state variables and state variables. So x1 dot, suppose I would like to have x1 dot here, x1 dot. So what are the branches connected and approaching that x1 dot? One is from x1 with -4, it's transmittance, so -4 x1, then 2 is from x2, so plus 2 x2. These are the 2 branches approaching x1 dot node, so I could write that equation. Similarly, I want to get x2 dot. x2 dot is the node here, so I want to write x2 dot. What are the branches approaching x2 dot? One is 3u and the other one is from x2, there is a branch with -8 gain. So I can say that 3u minus 8 x2. So this is x2 dot, you could get now as 3u, this is the branch, 3 times u, and -8 times x2 you could get. The third differential state variable is x3 dot. So what are the branches approaching x3 dot? One is from u with 6 as its gain, so 6u, then -12 from x3, so -12 x3. So this is the way you should write all the 3 equations, first from the given graph. Now all these 3 equations must be represented in the form of matrix. So all differential state variables it is 3 cross 1. Now, the coefficients of all these three equations we must represent. For x1 dot, first row is -4, 2, and then there is no x3 component. And for x2 dot, it is 0, -8, and 0. And for x3 dot, 0, 0, -12, whose dimension is 3 cross 3. Now, state variables x1, x2, x3 is 3 cross 1. Now, the input matrix, when you look at the coefficients of u in all the three equations, there is no u coefficient in the first equation, so it is 0. And in the second equation, u coefficient is 3, and in the third equation, 6 is the coefficient and multiplied by u. So this is the state equation, and this is the output equation for the given signal flow graph. Another variety of the problem, that is system described by the signal flow graph, and we need to get the state model for this. And when you look at this node, x1 dot is differential state variable, and this can be written as x1 dot. There is one path coming from x1 with -1, so minus x1. Then there is another branch approaching from x2 dot with 1 by s, so plus 1 by s into x2 dot. This is minus x1 plus 1 by s, and x2 dot is nothing but s into x2, so ss gets cancelled. This is equal to minus x1 plus x2. So x1 dot is given by minus x1 plus x2. When you look at this node, it is given by x1 dot plus x1. So what is its resultant? When you replace x1 dot by minus x1 plus x2 and x1, so this node is now x2, is nothing but minus x1 dot plus x1. So now the another node you have got here is x2 dot. x2 dot, this is equal to, from x1 there is a branch coming with -1, so minus x1, and the other one is from input you have got with 2, so plus 2 times u. So you have got two equations now. One is x1 dot given by this and x2 dot given by this. Now you need to form the state model. So x1 dot, x2 dot is equal to, and the components of this is -1 and 1, -1 and 0, and x1 and x2. So you can see x1 dot equal to minus x1 plus x2, that is the first equation, and x2 dot is equal to minus x1, and there is a 2u also, so we must have the input matrix with 0 and 2 and then u. So the output equation y is equal to, you can see here output y is connected from x2 with 0.5 gain. So I can say that it is 0 and 0.5 and x1, x2. So this is the way the state model is to be obtained for the given signal flow graph. So how to obtain the state model when electrical network is given? Electrical network, generally it consists of memory-less elements like resistors and energy storage elements, inductors and capacitors. So to form the state model when electrical network is given, we need to know certain points like what are the state variables. State variables are nothing but voltage across capacitor and current through inductors are considered as state variables. And how many state variables a given network has? So, the sum of inductors and capacitors are given by number of state variables. Now, you need to apply Kirchhoff's laws, KVL and KCL to the network and get the equations in the form of voltage across capacitor and current through inductors. So, KCL should be applied at capacitor junction and KVL should be applied through inductors in a loops, and the resultant equation should consist of differential state variable vector, state matrix, input matrix, input vector and output vector, all this. So, when electrical network is given, we need to look into the network how many inductors and capacitors it has. Based on that, state model can be framed. So, for this given electrical network, how to obtain the state model? You can see here the number of inductors in the network are 2 and 1 capacitor. So, state variables have to be chosen first. They are nothing but current through inductors and voltage across the capacitors. So, the state variables for this network are current through inductor IL1 and IL2 and voltage across the capacitor. Now, we need to apply KCL at the junction where you have a capacitor. So, apply KCL at the junction. You can see there are 3 currents, IL1 and IL2, and current through this capacitor you can consider as IC. So, you can write this current through the capacitor is IL1 minus IL2. So, this is the KCL at capacitor junction, and the current through the capacitor you can write as C into dVc by dt, because voltage across the capacitor is the state variable. So, I would like to have the equation in the form of state variables so that I can form the state model easily. Now, the 2 currents IL1 minus IL2. So, you can have this dVc by dt is derivative of this voltage across the capacitor as Vc dot. Vc dot, capacitor C value, take this other side and it is equal to IL1 by C minus IL2 by C. So, this is equation 1. Using KCL, apply at the junction where you have a capacitor, and then you got one equation for one state variable Vc dot. Now, let us apply KVL to the 2 loops which we have, and then we get an expression for current through inductors. So, KVL 1 is for this particular loop. So, you can write this as Vi is the input voltage here, R1 IL1 current in the loop you can consider as R1 into IL1 plus L1 into dIL1 by dt plus voltage across the capacitor. So our interest is the derivative of this inductor current as differential state variable. So I want to have this as IL1 dot, that is equal to VI by L1 minus R1 by L1 into IL1 minus VC by L1. Call this as equation number 2. So I could get IL1 dot, one of the differential state variables. Now I need to apply KVL2 for the third equation. So KVL2 I need to apply. For this, the voltage across the capacitor VC is equal to IL2 L2 into dIL2 by dt plus R2 into IL2. So again I need to get this equation in the form of differential state variable, the second current. So IL2 dot is equal to VC by L2 minus R2 by L2 into IL2. Consider this as 3 equation. So all these 3 equations now must be put in the form of matrix form, that is nothing but state model. So the state model using these 3 equations, you will get first a state equation. I have 3 variables. So differential voltage across the capacitor, current through first inductor, current through second inductor, forming the differential state vector of 3 cross 1. This is equal to, now the coefficients of the equations in the right hand side should help us to get the state matrix. There are 3 rows and 3 columns, 0, 1 by C, minus 1 by C, minus 1 by L1, minus R1 by L1, 0, and 1 by L2, 0, minus R2 by L2. So this is the state matrix you get, and 3 state variables like this. You have VC, IL1 and IL2 plus the input matrix is 0, 1 by L, 0 into U. So this is called as state equation you get. Now I want to get output equation. Is simple, that the voltage across this resistance is nothing but output voltage. So IL2 multiplied by R2 is V0. So you can get the output equation Y is equal to 0, 0, and only resistance is there across the output. So VC, IL1 and IL2 is the output equation. So this is the way. Choose the state variables as current through inductor and voltage across the capacitor. Write the equations using KCL and KVL and put them in the matrix form. You get the state model. Now let us see how to obtain the transfer function when the state model is given. Any linear time invariant system, it can be described by its transfer function or even it as a state model. That's why there is a relation that exists between transfer function and state model. So when transfer function is given, a state model can be obtained, and when state model is given, transfer function can be obtained. So if you want to analyze the stability of the system in the form of state model, then let us convert. If the transfer function is given, converting into the how to obtain the transfer function when the state model is given. When we feel that analysis is easy in the transfer function approach, so how to obtain the transfer function is our question. Now, as you know that state model will have 4 matrices. State model will have 4 matrices A, B, C and D. They are the matrices that appear in the state model. Now, to get a transfer function, there is a relation that exists. That transfer function is given by C matrix, then Si minus A inverse into B matrix plus D matrix. So, to get a transfer function, I must know all 4 matrices. That means state model I must know, and this is the relation. So, this is nothing but C, Si minus A inverse is nothing but adjoint Si minus A by mod of Si minus A, the determinant, multiplied by B matrix plus D if that exists in the system. D is a transmission matrix and that appears only when you have an active elements in the circuit or network. So, in this, the denominator of the transfer function is determinant of Si minus A equal to 0. This is known as the characteristic equation. This is known as the characteristic equation. So, as when I say that this is a characteristic equation, the roots of this equation are nothing but the closed loop poles. They are nothing but closed loop poles because denominator is a characteristic equation, and they are also called as eigenvalues. So, the roots of Si minus A determinant gives you closed loop poles. They are nothing but eigenvalues, and then you can find out that way. Now, let us find the transfer function when the state model is given in the form of A, B, C, D matrices. So, the state model is given here in the form of state equation and output equation. Now, we need to get a transfer function. So, find transfer function. Now, this matrix is A and this is B and this is C. No D is given here, only A, B, C matrices. Now, the formula for the transfer function is C, then adjoint Si minus A by determinant of Si minus A into B. So, I need to know what is Si minus A. So, A is given here. Then what is Si? So, Si minus A is nothing but S0, 0, S. This S is multiplied by identity matrix, and then minus, you have A here, minus 2, minus 3, 4 and 2. So, you need to get Si minus A by subtracting this matrix and this matrix. So, you get this as S plus 2, then 3, then 0 minus 4, so it is minus 4, S minus 2. So, this matrix is nothing but Si minus A. And how do you get generally this matrix from A? So, when you look at A, you can remember how to get Si minus A. Diagonally, you are adding S diagonal components, S is added, and there is a sign change for this diagonal elements. So minus 3 has become 3 and 4 has become minus 4. That way you can get Si minus A directly by looking at the A. Now once you get Si minus A, we need to have what is adjoint A and determinant A. So the transfer function is given by C matrix first. C is given by 1 and 1. Then adjoint A for this Si minus A, that adjoint of Si minus A is obtained in this way, that S minus 2, then minus 3, then 4, then S plus 2. This is adjoint Si minus A into B, that is 3 and 5. So C into adjoint of Si minus A into B divided by determinant of Si minus A. So determinant of this particular matrix, product of this minus this, it gives you S square minus 4 plus 12. So you get determinant of Si minus A as S square plus 8. So this transfer function, you get product of this, then multiply this to this matrix and then multiply this, you get 8s plus 1 divided by S square plus 8. So the transfer function is given by 8s plus 1 and S square plus 8 is nothing but there are two poles on j omega axis. Now you could get the transfer function which consists of zeros and poles. So where are the poles? The denominator part is actually known as the characteristic equation. The denominator part is actually known as characteristic equation. It is equal to S square plus 8 equal to 0. So S is equal to plus or minus j root 8. So there are two poles located on j omega axis. So that means in the S plane you can mark the two poles. One is plus j root 8 minus j root 8. So the nature of the system, which is described by its state model, stability aspect, is, we can say, it is a marginally stable system because the poles are on j omega axis. So this is the way you should substitute in the formula to get the transfer function, and that needs all the four matrices A, B, C and D. So this is another problem. The system is described by its state model, and this is A matrix, this is B matrix and this is C matrix, and you are asked to find out the transfer function for this second order system. So this is given by C adjoint Si minus A by determinant into B. So Si minus A is required first with the help of A matrix. So this is S0 0S minus the A matrix that is given here 0 3 minus 2 minus 5. So this is equal to S, then minus 3, then 2, then S plus 5. So you get Si minus A as 4 element, you can see. Now I want to get for this adjoint of Si minus A. So the procedure here to get this adjoint just interchange these two elements s plus 5 and s diagonally and change the sign. Change the sign, minus 3 has become plus 3 and this becomes minus 2. So this is adjoint of Si minus A. Diagonal interchange and this diagonal just sign change. Now the determinant of Si minus A is also required for this, and this will be s into s plus 5 and minus 3 into 2. So you get s square plus 5s plus 6. This is the determinant of Si minus A, which is nothing but the characteristic equation. Now the substitution of C and B and all these 4 parameters to get the transfer function. So the transfer function is nothing but C matrix is given by 2 and 1. Then adjoint A you got this one. So that is given by s plus 5, 3, minus 2 and s. This is adjoint A, and B matrix is 1 cross 1, 1 by 1 divided by the determinant of this Si minus A as s square plus 5s plus 6. Now you multiply these two matrices, then the resultant is with this. So you get the transfer function as 3s plus 14 divided by this characteristic equation. When you factorize this s plus 2 into s plus 3, you get. So finally it leads to numerator term and denominator term you get, and we are interested in the denominator part, the characteristic equation s square plus 5s plus 6, and the closed loop poles are at minus 2 and minus 3, and the 0 is located at s is equal to minus 14 by 3. So the system represented in the form of poles and zeros in the S plane. At minus 2, at minus 3 you have a poles, and at minus 14 by 3 you have a 0. So as it is in the transfer function, you are not finding any constant or coefficient, gain constant. So we can say that the poles and zeros are on the negative real axis. So the system is, as it is, over damped system because poles and zeros are on negative real axis, and we can say that it is a stable system which is represented by a state model. So this is the way we should obtain the transfer function for the given state model using appropriate equation.